Assalamu alaikum wa rahmatullahi wa barakatuh. How are you guys? Continue with chapter 3 today, and then at the end, it's about 10 minutes to the time, we will have our quiz 2. Okay. We will have our quiz 2 at the end. Okay. I hope you have seen the major 1 schedule. M1 for this course is coming next week on Tuesday, 12 to 1. The venue is also there, 060. Okay. All right. Let me move on. Yesterday we have here. Yeah, we have to start the definition. Here we'll look at fluid statics. Okay. Definition: fluid particles, a body of fluid having finite mass and an internal structure but negligible dimension. This we discuss about particles in statics, is it? Where we approximate a body to, where we consider the body's property, the body to be made up of just a mass, or by neglecting the dimension. Okay, that is, we assume it is very small. This will help us in our analysis. Okay, and pressure is the ratio of normal force applied to area at a point, or pressure is the compressive force per unit area, because pressure is always compressive. Okay, not tensile. It's the compressive force per unit area. Is that rest or sufficiently slow so there is no relative motion between adjacent parts of the body, meaning they are moving with uniform velocity. Okay, because statics is a study of bodies either at rest or moving with uniform velocity. Okay, let me see. All right. Okay, so uh, then the hydrostatic condition, it occurs when each fluid is in force equilibrium with the net force due to only pressure force balancing its weight. So hydrostatic equilibrium is achieved when the net force of the fluid particle is balanced by the pressure force only. And of course, because it's static, the particle's acceleration is 0. Okay? So this is when we say a hydrostatic condition exists, when the force of the fluid particle is in equilibrium with the pressure force. Meaning it's only the pressure force that is holding the fluid particle. Okay. If you look at this particle shown in this figure, we consider the particle and we have the pressure distribution, the vertical pressure distribution in this case. Then we isolate the free body diagram. You have the weight acting downward. Weight always acts downward. This is the fluid particle. And you have the net pressure force. We say net because you have it acting from the top in the downward direction and upward direction. So net meaning the resultant pressure force. Okay, so in this case, the weight of the particle is equal to the net pressure force acting on the body. And if a fluid is flowing, then the hydrostatic equation will sometimes apply. Okay, it will sometimes apply. And here, if you look at this figure, you have uh, water flowing in a pipe. Okay, and why pressure force balances the weight force for each fluid particle is that it balances the weight for each fluid particle that is situated on one of the planes. Okay, so for any single plane you consider, the weight particle is
Doctor,
also a hydrostatic condition. Okay, when you consider some vertical section, yeah, these are examples of planes. Okay,
Doctor, I have a question here.
okay, what is it?
You said if a fluid flowing, then the hydrostatic equation will sometimes apply.
Yes.
But then first slide you said it's study the fluid body that are at rest.
No, or moving sufficiently slow. Let me go back. Or moving sufficiently slow such that there is no relative motion between adjacent parts of the body. Because the first one, yes, I said at rest. Let me try to. Why is it not? I want to write.
So it's at
Okay, it
rest
is.
and when it's moving
Yes.
slowly.
So first one, if you look at it, is at rest or moving sufficiently slow. Okay, or
Okay.
moving sufficiently slow so there is no relative motion between adjacent parts of the body. Okay, if it's moving very slow such that there is no relative motion, such that the velocity variation is very small in that case, so it can also be said to exist, and that is why we get this example here. Okay, this is at rest, first instance. This is in motion, but moving sufficiently so such that the weight force for each fluid particle is balanced exactly by the pressure force on one of the planes. Okay, so when you consider a vertical plane, hydrostatic condition prevail on this plane and also on this plane. Okay, here piezometer, we are going to explain what that means. It's a simple, a small pipe that shows that all that is used to find the pressure head at that point. Okay.
Okay, okay, thank you, doctor.
You're welcome. But why is my pen not working? Now, let me, I don't know why it is, but sure, in the actual one, it will not be this distorted. It will not be distorted as you see it here. Okay. So here, pressure is the ratio of normal force applied to area at a point. I told you before that pressure is the term is used to apply for fluid only. Okay, usually for fluid. For solid, is equivalent to normal force. Okay, that is the force acting perpendicular to an area. That is for solid. Okay, while for fluid particles, we call it pressure, which is the compressive force acting per unit area. Okay, so pressure here is, the limit when you consider a particle, the normal force acting per unit area. As the area, attains delta A tends to zero. That is acting on a particle. Here we are considering a particle, and then we look at the whole body. When we integrate, we can now like approximate the pressure to be force over area, the average force or the net force acting over the area. Of course, the force has to be perpendicular to the area. That is the assumption in simplifying this equation. And we have already explained that in chapter 2. So here we are looking at, if you look at this body, okay, this is the pressure distribution acting. If you look at this small area at this point, okay, look at this area, the force acting per area, the resultant force, normal force over the area gives the pressure acting. Pressure is always compressive, okay? It's a compressive force. Now, relating pressure to force. Of course, pressure is force over area, so pressure force is now pressure times area, simple, okay? So here, the force is the integral of the force over area dA. That is summing it up, that is integration. We are summing around all the particles, all the sides. Okay, the force over area, then we multiply by dA. Okay, so here we have dF to be equal to, this is the pressure distribution, how pressure varies from point to point along a surface. And in this example, pressure is large in front and low in back. Okay. And at this point, you see the normal force acting perpendicular to the area. Okay. You have N to be the unit vector that is outward from the surface. And the pressure is in opposite direction. The force, normal force is in opposite direction to the unit force, to the unit vector. Okay, that's why you have this negative sign, because the F and N have opposite direction. Okay, that is the direction of the F is in opposite to that of N. Okay, so the F is minus P N dA. Okay, and then the pressure force, when you integrate, when you integrate this now, okay, you have the pressure force, which is this, which can be simplified to just be pressure times area. And what are the assumptions? This we discussed in chapter 2. The assumptions in having this simplified equation. I hope you can still remember the assumptions. Okay, and pressure can be expressed in two different ways. I mean, the unit of expression, the pressure force. You can express the SI unit. It has about 2 SI units, Newton per square meter, because Newton force, meter square area, force per unit area. So Newton per square meter, and Newton per square meter is equal to Pascal. Pascal is the name of the scientist who worked so much on that area. Okay, so 1 Pascal is equal to 1 Newton per square meter. Okay, that's why example 25 Newton per square meter equal to 25 Pascal. And then we have the US customary system of unit, which is pound force per feet square. Okay, pound force, that is the F, pound force per feet square. Sometimes it is simply written as pound per square feet, or sometimes it's written as PSI, or inch, pound force per square inch. Okay, so PSI, I don't know why it's not writing. Well, let me see if it can write on the whiteboard. No. Okay. You know, Firefox on the Chrome, I was using Chrome, but then I tried, but now with this Firefox, maybe I will switch to see if things will work better. Okay, so PSI, pound per square inch, is the US customary unit, and you have PF sometimes, pound per square feet. Okay, and it can be expressed as a height of a column liquid such as water or mercury, a meter or feet or inches or other unit. Okay, here, as we are going to see, when you fill a mercury and invert it, you know, the pressure, the atmospheric pressure will balance. Okay, will hold the mercury height of the water column. We are going to expatiate more on this in the subsequent slides, how this happens. Okay. And pressure here is expressed is using the height of column of mercury or water is called head. Okay, so for instance, we can say 3-meter head of water. Okay, and here we are referring to pressure. We're expressing the pressure as 3-meter head of water. And the conversion, 1 atmosphere, when you fill a glass bowl, in this we already did it. Okay, we will explain this more in the uh, pressure measurement. Okay, the pressure measurement. Okay, when you have a bulb, let's say a glass tube, you fill with mercury, you have like a container, a beaker of mercury, you invert it. When you invert it, that is upside down, and place it inside, then the atmospheric pressure will sustain a height of 760 millimeter of mercury. If it is water, it will be 10.33 meter of water. That's very high. Okay, and 1 atmosphere is equal to 10.33 meter of water, and 1 atmosphere is also equal to 760 millimeter of mercury. And also 1 atmosphere is 101 kilopascal, 101 because the practical pressures we have normally they have higher values. So normally we will be expressing pressure in kilo, okay, kilopascal or kilonewton per meter square, okay. And here, the same atmospheric pressure for mercury, it can hold a weight of mercury up to this height, 760 millimeter, less than 1 meter. But for water, it has to be 10.33 meter of water. Who can tell me why this is the case? Why is it that, I mean, the same 1 atmosphere is equal to 10.33 meter of water, and the same 1 atmosphere is equal to 760 millimeter of mercury? Hmm? Who can help in telling me why this is the case? We did density, isn't it? This is because of the density. Density of mercury is about 13,500 kilogram per meter cube. That of water is 1,000. So mercury is almost 14 times denser than water. Okay, it's almost 14 times denser than water. And that is why here also the, what do you call it? The height to which water can be sustained, if you divide 10.33 over 0.76, is also almost the same. Okay, about 13,600. Okay, almost 14 times. Okay, almost 14 times. This is solely dependent on the density because mercury is heavier than water. So for that, 1 atmosphere can support a height of mercury that is just 760 millimeter. While the same 1 atmosphere, if it is water, because it is less dense, it is lighter, it can support up to 10.33 meter of water. This is entirely dependent on the density of the liquid. Okay. Of course, I can ask you to now ask you, based on this, what about 1 atmosphere will support, like if you have let's say gasoline, okay, let's say fuel, benzene. So 1 atmosphere will support what height of benzene? All you need to do is to look at the density. What is the density of benzene? And then based on the density, you compare the density, you compare it with either that of water or mercury, and then based on the ratio, the number of times that either mercury or water is denser, then that will be the equivalent height that it can raise, or inversely proportional, because the less dense it is, the higher the height. If it is lighter, it will support much higher height. If it is heavier, it will support less depth. That's why in mercury, because it is heavier, the depth to which, or the height to which it can rise, or the 1 atmosphere can support is only less than 1 meter. 760 millimeter. While for water, because it is lighter, 1 atmosphere can support a height of 10.33 meter. Okay, and other units, practical units for pressure is bar. Okay, we use bar. 1 bar is 10 to the power of 5 Pascal. 1 bar is 10 to the power of 5 Pascal. Okay, and 1 kilogram force per centimeter square, which is another unit of pressure, is also almost equal to 1 bar or 1 atmosphere. Okay, so note that the pressure units bar, atmosphere, and kilogram force per centimeter square are almost equivalent to each other. You know, when you use your tire gauge, if you look at it, is graduated. You have 2 units, one in bar, the other one in I think is PSI. Yeah, PSI. Okay. Now, example 1, if a steel plate is experiencing a pressure head of 5 meter of water, okay, a steel plate is experiencing a pressure head of 5 meter of water. How can you express the pressure on the plate in SI units? I think, let me open the slide here so that I can write, because I cannot write with my pen in the presentation mode. I don't know why. So let me open the file and share the screen, probably so that I can write something in the slide. Did I jump some slides? Wait, I can see some slides here that are not. Uh, please hold on. I'm seeing some missing slides. I don't know what happened. There are some slides that are not showing. Sorry, I think I will just share the slide because this one, I don't know what happened, but it's not showing. Some slides are missing here. So let me just share. Okay, so now, all right. So, like I said, I just realized that some slides are not showing. So, yeah, for situations similar to those shown in the figure, you can apply the hydrostatic equation, and this is the hydrostatic equation. That is P equal minus rho G delta Z. Okay, this is the hydrostatic equation. We are going to talk about this hydrostatic equation in greater details later. So this can be applied to points situated in a plane, like in this vertical plane. All we're saying is that the change in pressure, or dP dz, is equal to minus gamma. Okay, minus gamma. Gamma is the specific weight. Okay, meaning pressure varies, it increases downward as Z decreases, P increases. When you go deeper down, okay, pressure is increasing while Z is decreasing. This, okay. Here, pressure resultant force is normal to the area and acts in the direction towards the surface. This I explained that is compressive. We speak of pressure only when we deal with a gas or liquid. Okay, the counterpart of pressure in liquids is normal stress. Okay, counterpart of pressure in liquids is normal stress. This I explained. It's always compressive towards the surface. Then pressure at a point is the compressive force per unit area, and it gives the impression of being a vector. Okay, it gives the impression of being a vector, but it is not, because pressure at any point in a fluid is the same in all directions. Okay, it's the same in all directions, meaning it has magnitude but no direction. Thus, it is a scalar quantity. If you look at the pressure acting at all points around the fluid element is P. Is the same, okay, is the same magnitude. Okay, so unlike force, if it were to be force, the force acting horizontally will be different from the one inclined, will be different from the its component, or a force acting with component horizontally and vertically that have different magnitudes. But pressure is not. Pressure has the same magnitude irrespective of the point that it is acting. That is irrespective of its angle of inclination. Okay, so pressure is a scalar quantity, not a vector quantity, because it is the same at all points. Okay, this is very important. And this can be proved. Okay, pressure at a point is the same in all directions. Okay, this is a simple example to prove it. This is a fluid element like a wedge in three direction. Although here we take delta y to be 0, sorry, delta y to be 1, that is the thickness which is into the page, like a 3D figure. Okay, so this is like the cross section, which is rectangular, delta x, delta here, and then we have delta z, and then we have delta y into the page, but it's assumed to be 1 here. So if you look at the pressure forces acting at the faces, the pressure force here will be the pressure times area, P2, the pressure acting on this face, the area, delta x, delta y. The same thing here, Py, delta y, delta z. This is P3, acting vertically along the plane. And the angle of inclination is theta in this case. Okay, let me reduce the thickness of the, okay, the angle of inclination here is theta. So when you resolve this using the force equilibrium, that is summation of forces in any given direction is 0, using either summation fx or summation fz. Okay, if you look at summation fx, so we sum the forces horizontally, and we have P1, or this one P1, we have P3, because P3 has components. The pressure force acting under at the inclined surface has component horizontally and vertically. Okay, so the horizontal component we use sin theta, the vertical component we use cos theta. But the vertical component, we also have the weight of the fluid element acting vertically downward. Okay, the weight of the fluid element, which is given by this one. Okay, mass times acceleration, or mg. Okay, and mass is what? Density times volume. So that's what you have the density, and this is the volume, delta x, delta y, delta z over 2, because it is the cross-sectional area times the depth. So that's why you have half, because area of a triangle is half base times height. Okay, so this represents the weight. So if you simplify this and set delta z to tend to 0, okay, if this delta z tends to 0, the weight becomes And when it becomes very small, when delta Z tends to 0, you will realize that this term will also tend to 0 as well. Okay, and then P2 will be equal to P3, and here P1 will be equal to P3 as well. So what we are saying is that at the end, you will realize that P1 is equal to P2 is equal to P3, and all we can represent it as P. That is why here we represent the pressure acting at all points to be equal to P at all points along or on the particle. Is it clear? But you know this is different if it were to be force, okay? Because the force acting, force is a vector quantity while pressure is a scalar quantity. So what we are saying is that the pressure at a point in a fluid has the same magnitude in all directions, okay? And this result is applicable to fluids in motion as well as fluids at rest, since pressure is a scalar quantity, not a vector. So whether it is moving or it is at rest, you have the same thing happens. Let me reduce the thickness of my pen. Okay. Yeah, now it's better. Okay. Yeah, this I explained about the pressure head. And here what we are saying, when you have a beaker, you invert mercury glass, mercury beaker. Okay. If this is mercury, then the mercury will rise up to a height of 760 millimeter. It will rise up to this height because of the atmospheric pressure acting on this face. Okay, it is the atmospheric pressure that will push the mercury and hold it against gravity up to this height. If it is mercury, if it is water, up to a height of 10.3 meter, 10.33 meter, that is like 14 times higher, 14 times higher. Okay. Now, on this example here, it says if a steel plate is experiencing a pressure head of 5 meter of water, how can you express the pressure of the plate in SI units? You have a steel plate experiencing a pressure of 5 meter of water. Okay, so this is the height. Okay, our height is 5 meters. So how can you express it in SI unit? So pressure, as we have seen in the hydrostatic equation, okay, dP dz, isn't it, is equal to minus gamma. And this simply means, when you go deeper down in a fluid, Z decreases while the pressure increases. So this is why we have the negative sign. So this we can approximate, D is just equal to minus gamma dz, okay? And this for fluid element, and then for the whole fluid, when we integrate, okay, we can have the pressure to just be equal to gamma z, okay? This is the simplification or approximation of this equation. Okay, we remove the negative sign because we know that, yeah, the pressure increases as the depth decreases, okay, and gamma is what? Rho g. So rho g, z is the depth, okay? So to convert it to pressure, z is provided here as the height. So all we need to do, the pressure in the SI unit, it is water. So gamma for water is 9810, isn't it? Times the height. Okay, so this is what you have here, 5 times 98. Okay, so this is almost 49. The unit Pascal. This can be changed to just 49 kilo Pascal. Is it clear? So this we convert the height. We express the pressure as using the head of water, okay? And here we converted it using this formula, using the hydrostatic pressure equation, okay? This is the hydrostatic pressure equation, okay? we converted it to pressure in SI unit. Okay, is it clear? Let me see. Can you? Yeah, you can see what I'm doing. So now let's move on. Pressure scales. Pressure can be expressed in 3 different scales. Okay. First, you have the absolute pressure, gauge pressure, and vacuum pressure. If you remember, I briefly explained what each one of these, what each one means before. Okay, we know that the first we know the atmospheric pressure. Okay, we know the atmospheric pressure, pressure exerted by the gases in the atmosphere. Okay, which is usually constant, most especially on the surface of the Earth. Of course, it varies with altitude. The higher you go into the atmosphere, the lower the pressure. But on the surface of the Earth is relatively constant. Okay, and it is exactly equal to 1 atmosphere or 101.3 kilopascal at sea level. At sea level. So this is the atmospheric pressure. Any pressure above atmospheric pressure is called gauge pressure. And I told you, the tire gauge, okay? The tire gauge that we use in measuring the pressure in our tire is set at, the gauge to measure the gauge pressure. Because in the atmosphere, ordinarily, it will show you 0, meaning it's atmospheric pressure. So there, our reference pressure is atmospheric. That's why it is 0. But anything above it, this is the atmospheric pressure here. Okay? Anything above the atmospheric pressure, we call it gauge pressure, P gauge. And then anything below the atmospheric pressure, vacuum, we call it vacuum pressure. But then we have the absolute 0 pressure, okay? The absolute 0 pressure, which is the pressure of the absolute vacuum, because pressure is due to the weight of the fluid acting per unit area. If you don't have any fluid, it means the pressure is 0. And in vacuum, you don't have any fluid. You don't have any fluid, no liquid, nothing, no gas. So that's why the absolute 0 is the pressure of the absolute vacuum. It's called the absolute 0 pressure. Okay. Atmospheric pressure can also be set as the absolute as 0 when you take it as the reference pressure. When you use the
Doctor,
atmospheric pressure to be, yes.
I'm sorry if you say it again. The pressure,
What?
vacuum pressure.
What?
Last thing you said, I did not understand.
Okay, I will go back to it. Don't worry.
Yeah,
Um,
thank you.
First, you understood the atmospheric pressure and the fact that we can set the atmospheric pressure to be the reference pressure. If it is set as the reference pressure, then it will be 0. Anything above it will count. We will start counting. This will be like our origin, okay, 0. Anything above will count, and this is when we use the gauge pressure. And anything below will be negative. This is when we use the vacuum pressure. That is one point. The other point, because atmospheric pressure also has value, it is not 0. Then what is the 0 pressure? That we call the absolute vacuum pressure, or the absolute 0 pressure, which is the pressure of a vacuum. Because pressure is due to the weight of the fluid elements acting on a surface area. So if the weight is 0, then definitely the pressure is going to be 0. So that is why this is the absolute 0, okay? P abs, which is the absolute 0, which is the main reference point for all pressure measurement. From here, the atmospheric pressure is measured. This is the reference for the atmospheric pressure. When you measure it, you have it, and its value is what? 101.3 kilopascal. Now, then any pressure measured using the absolute 0 as the reference point is called the absolute pressure. Now, at the atmospheric pressure, which is at this point, what is the absolute pressure? Is the same, meaning the atmospheric pressure at the absolute pressure at this point at PAM is equal to the absolute pressure, which is 101 kilopascal. What we are saying is simple here. We use two reference pressure points, or two reference pressure points to measure other pressures. One is the absolute pressure, which is the absolute zero. From that one, the one we measure are usually two. When we use the first one, this is the first one, this is the second reference. When we use the first reference, basically here we measure two types of pressures. One is the absolute, two is the atmospheric. When we use the first one, we measure the absolute pressure, which is the pressure from the zero that goes up, okay? And then we measure the atmospheric pressure using this reference. You can see the atmospheric pressure, the reference is here, its value is 101. Now, there is a point when the absolute is equal to the atmospheric at this point. At this point, absolute pressure is equal to atmospheric pressure because atmospheric pressure is constant, but absolute pressure is just any pressure you measure above the absolute zero pressure. That's it. When it is at the atmospheric level, then absolute pressure becomes atmospheric pressure. Is it clear? Now, when you now use this second scale or the second reference point, which is the atmospheric pressure, when you use it as the reference point, then you can measure again two types of pressure here. One, you can measure the gauge pressure, which is the pressure above atmospheric. And then you can measure the vacuum pressure, which is the pressure below atmospheric, which is negative. It's negative or it's negative gauge. The positive one is positive gauge. The negative one we can say negative gauge, or we can remove the negative sign and just call it vacuum pressure. But absolute pressure is always having the reference point 1. This is the reference point for absolute pressure. And like in this is the absolute pressure. You can see where it is starting, the arrow going up. The vacuum pressure, it starts from the atmospheric pressure, the arrow going down. The gauge pressure starting from the atmospheric pressure and the arrow going up. Okay. You can also measure absolute pressure above atmospheric, like here. So in this case, the absolute pressure is equal to atmospheric plus gauge. Because here, from here to here is atmospheric, then from here to here is gauge. While in this case, if the absolute pressure is less than atmospheric, then atmospheric pressure now is equal to absolute pressure plus vacuum pressure. Let me go to the next slide to show you these equations. All right, let me use this. Still on the pressure scale, this is very important. You need to really understand the graphical representation of the pressures, okay? You need to understand it very well. Pressure can be expressed, okay, in the three scales. I'm still explaining again. 1 atmosphere is equal to 101.3 kilopascal or 14.7 psi, pound per square inch, or 33.9 feet of water, which is the same thing as 760 millimeter of mercury, or 10.33 meter of water. Because this one 3.9 feet of water is the same thing as 10.33 meter of water. When you convert 10.33 to feet, you get 33.9. And PSF is pound per square feet. So here we mix, the SI and the non-SI unit to express the atmospheric pressure. Okay. Now, when you look at this figure, we are still saying the same thing. This is our first reference point. This is the second reference point using the local atmospheric pressure. Okay. At this point, because this is gauge reference, that's why it is called gauge reference, because the atmospheric pressure is the gauge reference, is the reference point for the gauge pressure. So that's why we set it as 0. That is why we set it as 0. So P equals 0 here, but 0 gauge, okay, which is equal to 101 kilopascal absolute. Because at this point, pressure is 101, is equal to the atmospheric pressure. But when the gauge pressure here at the atmospheric level is 0, okay? Now, this is the absolute 0. Here is the absolute 0, so it's absolute 0. P equals 0 Pascal, absolute. So here, because the atmospheric pressure is constant, so we cannot say what is atmospheric pressure at this point because it is not variable. Atmospheric pressure is always 101 kilopascal. But now, from this, when you go down, you can see this is from here to here is 50 kilopascal. So this is, we can call it minus 50 kilopascal gauge, minus 50 kilopascal gauge, or we can call it 50 kilopascal vacuum. If we say vacuum, we don't need to write it as negative, okay? Because by definition, vacuum means negative pressure below, or pressure below atmospheric. So we use the symbol negative, we know it is negative or negative gauge. Here we can call it negative minus 50 kilopascal gauge, or is equal to just 50 kilopascal, and then we put vacuum. When we put vacuum, we don't need to write the negative sign. Is it clear? We don't need to write the negative sign because by definition, vacuum is negative. Okay, of course, having this is gauge and vacuum reference. This one, you can see gauge reference. So it is gauge and vacuum reference point. Now, this is the local atmospheric pressure. The value is 101. Okay, so if the gauge pressure is, so if the vacuum pressure is 50, what is the absolute pressure? The absolute pressure is the remaining pressure from the zero, from the absolute zero. And the total from here to here is what? 101. You take out 50. What is the balance? You have 51, which is absolute. Okay, ABS. Okay, so you need to indicate absolute vacuum gauge. This is 51 as absolute plus 50 as vacuum will give you the atmospheric pressure. Very simple. Now, this is 200 kilopascal gauge, meaning it's above atmospheric. This 200 kilopascal gauge, okay, it is above atmospheric. If we want to find the absolute, the reference has to be from the bottom, from the absolute, in which case we need to, from here to here, 100, and to here is 200. So that will give us 301 kilopascal absolute. Okay, I will take some other examples, don't worry. Now, on the formula, still, pressure absolute is equal to the atmospheric pressure plus gauge. That is, if the pressure you are measuring is above the atmospheric pressure, like in this case, you have gauge pressure, okay? Like in this case, the pressure, you can see the pressure value is above the atmospheric pressure. So in this case, you need to use this formula, that the absolute pressure is the sum of the atmospheric pressure and the gauge pressure, okay? Now, if the pressure you are measuring is below the atmospheric pressure, then in that case, you have to use the second equation, which is you have to use the vacuum pressure. So at that point, the absolute pressure is simply the atmosphere minus the vacuum pressure. We say minus because I said initially by saying vacuum is minus, so we don't put the negative sign attached to the magnitude. Okay, and this is just like in this case. When you have vacuum pressure to be 50 kilopascal, what is the absolute pressure? Okay, you simply, this atmospheric pressure is 101 minus the vacuum pressure is 50, and that's why we got 51, which is exactly what you have here. Okay, and we should know that the vacuum pressure is equal to minus negative gauge. Okay, this is the reference for the gauge pressure. Anything above is positive gauge, anything below is negative gauge. So we call it negative gauge or vacuum pressure. If you use the negative sign, then you just write gauge, like in this case, minus 50 kilopascal gauge. If you use vacuum, you don't need to write the negative sign. You just say 50 kilopascal vacuum. You don't write the negative sign. Please, you have to understand this very well. It is very simple, but you need to really understand all these simple calculation, absolute, gauge, and vacuum. Now, vacuum pressure, when pressure is less than atmospheric pressure, it is described using vacuum pressure. Okay, not because vacuum, definition of vacuum simply means you don't have any air inside, no air, no gas. So here when we say vacuum pressure, we are not referring to the absolute vacuum, okay, but we are referring to a state in which the pressure is less than atmospheric. The absolute vacuum is the one in which there is no air, no any gas. In that case, it is absolute zero. There is nothing active, okay, no matter. But when we say vacuum pressure here, we mean less than atmospheric pressure. And vacuum pressure is the difference between the atmospheric pressure and the actual pressure. The actual pressure at any point in time is the absolute pressure. Any other one is like relative. The vacuum pressure is relative with respect to the atmospheric pressure, as well as the gauge pressure is with respect to the atmospheric pressure. But the atmospheric pressure itself is with respect to the absolute zero pressure. Okay, so the pressure, the actual pressure at any point in time is described using the absolute pressure. Then it depends. Is it below the atmospheric? Then you use the second formula. If it's above atmospheric pressure, you use the first one to find the absolute pressure. Let me see what you are writing. Okay, all right. Now, still trying to explain, this is our absolute zero, the absolute reference. This is our atmospheric pressure, which is 101 kilopascal absolute, which is 101 kilopascal absolute, and this is 0 Pascal gauge. Okay, 0 Pascal gauge, and also 0 Pascal vacuum. Because atmospheric pressure is the gauge reference as well as the vacuum reference. So below it, you have minus 50 kilopascal gauge, which is 50, like I mentioned before, Pascal vacuum without the negative sign. And the absolute pressure here will be the difference between the atmospheric pressure and the vacuum pressure, which is 51. And if it is above atmospheric, this is gauge. Okay. And to find the absolute, to express the absolute pressure here, we say the pressure here, which is atmospheric, plus the gauge pressure, okay, which is this one. So let's take 5 minutes break, and when we come back, we will take this example again, all trying to demonstrate how to find the gauge pressure, vacuum, absolute, and all that. Okay, so let's take like 5 minutes break. Okay, gentlemen, let's continue. Right here, this example says, sketch the following pressures in all forms, scales, that is using absolute gauge and vacuum. So express and sketch them, meaning you have to show them that diagram, okay, using the different reference points or references, the absolute and the atmospheric. So first one says 20 kilopascal absolute. So here we want to determine the gauge pressure as well as the vacuum pressure. Okay. So 20 kilopascal absolute. This is the absolute zero. This is the atmospheric pressure, PTM. Okay. So we have what? Absolute to be 20 kilopascal. Absolute is always with respect to the zero absolute pressure. Okay, so 20 kilopascal absolute implies it is starting from the first reference point. Okay, so this is 20 kilopascal. Okay, 20 kilopascal. So how do we express the other, the vacuum pressure? The vacuum pressure is from here, isn't it? Which is going to be the atmospheric pressure minus the absolute pressure using the second. Okay, so absolute here is 20. Okay, atmospheric pressure is 101. Okay, and we get the vacuum pressure or the gauge pressure as the case may be. Okay, so here in this case, this is absolute pressure, this is the atmospheric pressure. Okay, if we use the first equation, we will get it in, it will be negative because it will be negative gauge. Okay, that's why we say 20 minus 101. Okay, giving us gauge. Okay, and gauge minus gauge is equal to a 20 kilopascal vacuum. We just remove the negative sign here. Okay, because I told you by definition vacuum is negative gauge. Okay, according to the top equation. So this is 20 kilopascal and this is 81. So you put 81 kilopascal vacuum, and that's it. And which is the same thing as minus 81 kilopascal gauge, and that is it. Okay. For the second one is 75 kilopascal gauge. 75 kilopascal gauge. For 75 kilopascal gauge, we have the absolute zero, we have atmospheric. This is gauge, so it is above atmospheric. Okay, so 75. And this is atmospheric. Okay, so we want to find the absolute pressure. The absolute pressure is the pressure at any point. So it's going to be the pressure here. Okay, what is going to be atmospheric 101 plus the gauge pressure. So we use this one, first equation. Absolute pressure is equal to atmospheric pressure plus gauge pressure. The atmospheric pressure 101, the gauge pressure is 75. Okay, so add them up, we have 76 kilopascal absolute. And here we don't have the vacuum pressure because it is not below atmospheric. Okay, it is not below atmospheric. Or sometimes you can say negative vacuum is now positive, using this equation. Negative vacuum is now positive gauge. So you can say, okay, vacuum now is minus 75, which is minus the gauge pressure. For the third one, 47 kilopascal vacuum pressure. 47 kilopascal vacuum. It is also similar. You start with the absolute and then you show the. Okay, so it says 47 vacuum pressure. So vacuum, it means it acts downward. So this is for. So to find the remaining absolute is going to start from here, which is going to be atmospheric minus vacuum. Okay, so we have to use this atmospheric. Absolute is equal to atmospheric minus vacuum. Okay, which is 54 kilopascal absolute. okay, which is
Doctor,
54 kilo. Yes.
in state 2, 75 gauge is equal to 75 vacuum, right?
What? What? What?
No, here vacuum.
Okay. So can you repeat what you just said?
It's equal to minus 75 gauge.
Yeah, minus 75 gauge. Yes. Yes.
So
You are right.
when we write it, we write the minus or just write
Yeah, yeah.
vacuum.
In this case, you can just leave it because normally when we say vacuum pressure, we mean the pressure below atmospheric. But mathematically speaking, based on this, okay, strictly speaking, you have vacuum to be minus. Okay, so it's going to be minus 75 kilopascal. So the vacuum pressure now is minus 75 kilopascal. Meaning if it is minus, it is referring to the gauge pressure, simple. The gauge pressure, if it is minus, is referring to the vacuum pressure. The vacuum pressure, if it is minus, is referring to the positive gauge pressure. Is that clear? Since the positive gauge pressure is the pressure above atmospheric, while the one below atmospheric is the vacuum pressure. So that's why they have the opposite sign. If one is positive, the other one has to be negative. So this is a simple way to put it. Is that clear?
Yes, it's clear.
Okay. All right. Now we move to hydraulic machines. Okay, hydraulic machines. Here we are still exploring the principles, I mean, of statics or the principles of pressure. Okay, the pressure in fluids. Okay, it is the principle by which pistons, pumps, and hoses work to transmit forces using fluids or energy to assist in the performance of a human task. Okay, we all use pumps, hoses, most especially in our cars, pistons. So this principle of hydraulic machines is used to transmit uh, forces using fluids or energy to assist in the performance of a human task. Because hydraulic machines, they make our task or work easier. They make our work easier. And for instance, you have the braking systems in cars, forklift trucks, power steering systems in cars, and airplane control systems. All these use hydraulic machines. More often than not, you have hydraulic fluid, because of the pressure transmission. We are going to learn something called the Pascal law, which states that pressure is transmitted at equal rate in a fluid system. And the main principle behind braking system. When you apply the brake, you have brake fluid. So you are applying pressure. So that pressure is transmitted to the brake fluid, which is transmitted equally towards all the tires. Okay, so as to now go and stretch the brake pad, and ensure that your car stops. Okay, and like I mentioned, the hydraulic machines adopt Pascal's law. Okay, it adopts the Pascal's law. Pressure
This
applied to an. Mm.
this
Go ahead. Mm.
this concept we use it for
Yes.
brake car,
Mm.
brake of the car.
Yes. 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 This we use the same concept for car brakes as well as power steering. As well as power steering, because your car has a power steering fluid as well, which you have to be taking constantly, to ensure that the liquid is within certain limit. Okay, so the main is the fact that pressure applied to an enclosed or continuous body of fluid, is transmitted undiminished. Undiminished meaning unreduced. Okay, so that is undiminished to every portion of that fluid and to the walls of the containing vessel. Okay, so this is simply the Pascal's law. Okay, and the hydraulic machine provides a mechanical advantage. Okay, a mechanical advantage is the output force over the input force, meaning you use small amount of force to lift heavy object. Okay, use small amount of input force to have a greater output force. Okay, using effort and load, meaning you, let's say you use 5 newton to lift 500 newton weight. Okay, so the mechanical advantage is 500 over 5, which is 100. So the mechanical advantage is like the advantage of using that mechanical system. Assuming I want to lift a weight, let's say this is a bag, 10 newton. This is the handle. I will have to use the same amount, isn't it, of force. I will have to use 10 newton to lift it, correct?
Yes, correct.
But when using a machine, here, simple machine, or if not simple machine, like a pulley system, you did this in statics. When I want to use pulley to lift this same 10 newton weight, I can apply 1 newton to lift it by using a pulley system. So that's why pulley is a simple machine. If you remember in chapter 7 of statics, that is under frames and machines. You can apply low amount of force to lift a much heavier, weight. So I can apply 1 newton to lift 10 newton. So the mechanical advantage here is the weight, the load over the effort. The effort is the applied force. Okay, 10 over 1, which is 10. Is it clear? Same thing in machines, okay, in the application of the brake system and what have you. And for the hydraulic machine, specifically we are referring to hydraulic machine. That is those machines, they work with hydraulic fluid. You have hydraulic fluid. And the basis here of using the hydraulic fluid is due to Pascal's law, that pressure applied to an enclosed continuous body of fluid is transmitted unchanged, undiminished to every portion of that fluid and to the walls of the containing vessel. We'll expatiate more in the following slides. Okay. In hydrostatic conditions, the fluid particles at the same elevation experience equal amount of pressure. This is another very important aspect under the hydraulic machine, or the concept that is being used. The fact that fluids at the same elevation experience equal amount of pressure. If they are at the same elevation, they experience the same pressure. We have seen from the hydrostatic equation, okay, the PdZ equal minus gamma. Pressure varies only with Z. It varies only with depth, okay? It doesn't vary horizontally. Pressure for the same fluid element, the pressure horizontally is equal. It changes only if the depth changes. If depth changes, then the pressure changes. That is, if the depth increases, the pressure increases. If the depth reduces, the pressure on the fluid element reduces. Is that clear? But horizontally, that is on the same elevation, fluid particles experience equal amount of pressure. So when you apply pressure to liquid element horizontally, that same pressure is distributed throughout an enclosed or continuous body of fluid. And this is the concept used in our pistons, in our pumps, in the power steering, the forklift, the braking system, and all that. Okay. Because fluid at the same elevation experience equal amount of pressure. And this is based on the static equation, okay? Now, to explain this further, we have water here in this container. We marked fluid elements A, B, C, D. So, for the first one, here we said, is the pressure equal in A and B? This is A and B. They are not at the same elevation. Okay, they are not at the same elevation, hence the pressure is not equal. Is the pressure equal in B and C? B and C, they are not at the same elevation, so they are not equal. Is the pressure equal in A and D? They are not equal. Okay, what about C and D? C and D are equal. Why? Because they are at the same elevation. Okay, pressure is highest at A because Pressure is just the weight of liquid acting on the fluid element per area. So if you go deeper, the deeper you go, the more amount of fluid you have acting. Like when you are at this point, at point C, you have only this amount of fluid acting. When you go deeper down to A, you have much more, larger amount of fluid acting on particle A than particle B, C, and D. And that pressure is highest at A. Okay, and that's why pressure increases with depth, because if the depth increases, you have more and more particles or amount or weight or force acting on the particle. Is it clear? And here at the top, of course, is only atmospheric, because it's only atmospheric pressure. So at the top, the pressure is atmospheric, while when you go deeper down, the pressure is above atmospheric in this case, because the pressure inside the liquid is higher than atmospheric pressure. So it represents the gauge pressure in this case. Okay, it gives us the gauge pressure. We will see some derivation very soon with respect to that. Now, still on the Pascal's law, I express it, an applied force is a pressure that it creates a pressure change that is transmitted to every point in the fluid and to the walls of the container. If you have this container, these are at the same height, okay? They are at the same height. So the pressure here is equal to the pressure here. It is P1 here, P2. So P1 is equal to P2 because they are at the same elevation. Okay, they are at the same elevation. Okay, so when you apply force here, okay, the force creates a pressure change that is transmitted at every point in the fluid and to the walls of the container. But at this point, for those particles that are at the same elevation, they have the same pressure. It helps us to lift heavier objects by applying small force, because once the pressure is the same, and we know pressure is force over area, then we can apply large force as long as the area is small. Or if the area is small, the force now is equal to PA. Okay, so since pressure is constant for the same elevation, so the force now is directly proportional to the area. Directly proportional meaning, like in the second part, this second case, you see area here is larger, so it means it can sustain heavier weight. For the first case, the area is small, so you can apply small force. Is it clear? You can apply small force here, say F1, to lift heavier force F2. This is F1, A1, F2, A2. F1 and A1, because of the fact that F1 is small, F2 is large, it can support huge, very large F2, because the force is directly proportional to the area. Because at these 2 points, the pressure is the same. P1 is equal to P2. So this will now make you have, if P1 equals P2, it means F over A1 is equal to F2 over A2. So here you can apply small force to lift heavier force. Okay, and here let's say F1 over F2 is now equal to A1. No, let me take it the other way. I want it F2 over A1, so it's now equal to A2 over A1. So the ratio of the forces, F2 is the output force, which is the load. F1 is the input force, which we call effort. Okay, it's A2 over A1. A2 is usually higher than, it has to be higher than A1. So this is called the mechanical advantage, MA, of the system. Okay, it means you apply small F1 to lift heavy object. And this is the same principle we use in our forklift and also in our jack, the car jack, the hydraulic car jack. Because you apply minimal amount of effort, minimal amount of force to lift your car that is, so many tons. Is that clear? This is because the pressure at the same point, okay, is the same. So you have the tendency, like this can be your your car jack, and this can be your car. Okay, this is the jack which has small area. You apply small force. This is your car having larger area, and you lift a heavier weight. Is it clear? We will expatiate this in the next slide as well. Now, still on the hydraulic, okay, so this is exactly explaining the car jack operation. This principle has been made use of in the hydraulic jacks that lift heavy weights by applying relatively small forces. So this is exactly the explanation, because of the fact that the pressure is the same at the same elevation. Even with slight change in elevation, the pressure remains the same, okay, for a slight change in elevation. But basically, at the same elevation, the pressure remains the same. And I said this is called mechanical advantage. Okay, so here you apply small force F1 to lift heavy load F2, because the pressure, they are at the same elevation. Okay, if it is at higher elevation, then P1, the pressure here, is going to support an additional height of the fluid, isn't it? Which is given by rho GH. Okay, which is given by rho GH, or just gamma H. This is P1 to P2 plus, this is P2 at the same elevation. P2 is here. But then, because the elevation is same, you have a weight that is supported again in addition to, because of this fluid. So you have rho GH. Rho is the density of the fluid. This is SG, specific gravity. And this is a hydraulic oil. So, meaning, in this case, what is the implication of having an oil? If the density of the oil increases, what will happen to the force required? Okay, what will happen to the force required? When you get P1 here, you now come and substitute it here to get the force needed. Okay, you come and substitute it here to get the force needed. So, meaning, when the density increases, the pressure needed to support the weight increases as well. Okay, meaning when the density decreases, you need less pressure to support the weight. And when you need less pressure, it means you will need less force. And that means the lighter the liquid, the less the force. The lighter the density, the less the density of the liquid, the less the force needed to lift heavier objects. You see, here it means when you put this hydraulic oil, it means when you put water here, the density, specific gravity of water is 1. So that means you will need more force. But when you put hydraulic oil, okay, whose density is less than that of water, you will require less force. Okay, and that is why in the hydraulic machines we normally don't use water, because if you use water, because water has higher density than the oil, so we will have less, we will need more force. But if we use an oil whose density is less than the density of water, then we will require less force, less amount of force. Okay, and here again, it means if it is reversed, if this is higher, okay, and this is lower, this is at this point, so it means P1 plus H will be equal to P2. Okay, so in this case, the pressure here P2, that is if the situation is reversed, okay, if this is higher. Now, still on the operation of a hydraulic jack, here we have a simple example, though it's just the explanation that I just gave. In this operation, when you consider a hydraulic jack being used in a car repair shop, we all have jacks in our cars. The pistons have an area A1 and A2, and the hydraulic oil, the specific gravity is 0.87. which is pumped in small piston on the left side, okay, and it slowly raises the piston on the right side. It raises the piston on the right side. A car that weighs 13,000 Newton is to be jacked up. At the beginning, when both pistons are at the same elevation, H equals 0, meaning there is no difference in the elevation. F1 holds the weight of the car, okay? F1 holds the weight of the car. And we have two cases that we want to find the amount of force needed, okay? The first case is when H is equal to 0. The second case is when H is equal to 2, okay? When H is equal to 0, so P1 equals P2. And of course, the oil is incompressible and the system is at rest, so we use hydrostatics. And the air density is negligible compared to oil density. Here we want to find F1, so P1 is equal to simple. We know F2 is given, A2 is given, F1 is given. We want to find F1, simple. So we make it the subject of the formula. So you see, when you substitute the value, and don't forget to make your conversion. This is in centimeter square, this is in meter square. Okay, you need to convert to the same unit. So we use 26 Newton to lift 13,000 Newton. You can imagine. We just use 26 Newton to lift 13,000 Newton. And so the mechanical advantage here is simply 13,000 over 26, which is very high. And this is because of the fact that the fluid pressure at the same point is the same, okay? And at the beginning, this is when H is equal to 0. Now, when H is not equal to 0, that is when H equal 2 meters, then in this case, P1 is equal to P2 plus rho GH. We need to include the height, okay? So P2 is equal to F2, and then the T is already given, okay? So F1, this is for the pressure. For the force, we multiply by the area, okay? By the area, so it will be P2 times A, okay? And P2 is just F2 over A2 times the area A1, and this one also times A1. And when we substitute values, we have 27, okay? So when there is difference in height, because we said at the same point, at the same elevation, the pressure is the same, okay? But when there is difference in height, when the other side is at a higher elevation, you need slightly more force to lift the same object. You need slightly more force. You can see 26 Newton in the first instance when H equals 0 and 27.4 Newton in the second instance. But when you look at 26 and 27.7, I mean, they are just approximately the same. Most especially when you compare the load that it is holding or it is lifting, which is the 13,000 Newton. 26 or 27.4 doesn't make any difference in that case. So that's why I said with the relatively small variation in the height, you have the same amount of, you need the same amount of force. Okay, so because of time, we'll continue here in the next class. Okay, and then we will now take our quiz. Yesterday, I did not schedule the makeup class because I felt it's better I deliver this class today, and then later today I can present the makeup class, so that you can have time later, maybe tomorrow, day after tomorrow, to watch the video for the makeup class, because it's very important. And our major is coming on Tuesday, and it's going to cover chapter 3, up to chapter 3. Okay, and I'm also going to probably maybe check to see if I can give you another homework now. Thank you.
Doctor, all chapter 3.
Yeah, it depends on where I stop from the makeup class. We lost 2 weeks. We lost week 1, isn't it? Week 1, because then it was scheduled, the course was floated lately. So we lost the whole of week 1. And then week 4, we lost the first lecture because of the problem we had with Blackboard that day, and then the second lecture because of vacation. So we lost 2 weeks completely, and this is week 5. Is it clear? So I will try to create the make-up lectures, and then of course, like I said, any one of you free at the time of the make-up lecture can be present if you have any question, or even if you are not present, you need to watch the video, go over it. If you have any question, you can contact me at any time. Okay?
We
Yeah.
have 6 lectures left.
What?
6 lecture left we have. Can you finish it?
6 lecture what?
Chapter 3. We have, I think, how many lecture?
Look,
11 lecture.
yeah.
Now we are in 5. So we have 6
Let's
lectures.
see what we can have in the makeup class, because these lectures are scheduled, based on 1 hour duration. So don't worry with the fact that, don't worry, anywhere we stop in the makeup lecture will be what will be examined in the major one. Is it clear? Okay. And for the quiz, I will just post it now on Blackboard. So all you need to do is solve it, and then take picture, send it to me on WhatsApp. Okay, so just send it to me on WhatsApp. Yeah, but make sure you write your name and ID at the top. Write your name and ID, and don't copy someone's work. You can see in the quiz one, most of you copied, and I get you. So try to ensure that you do your own work. Is it clear? And you have just 10 to 15 minutes to send me the final result on WhatsApp. Okay?